In this lesson, we're going to take a look at how we can use the changing concentrations in a reaction to figure out an equilibrium constant for the reaction, or how we could take an equilibrium constant and figure out concentrations. So we're going to use a tool called ice tables, and we're going to examine how concentrations of these products and reactants change throughout a reaction to do a little math. These are not too complicated. So we know when a reaction progresses, the concentration of each species changes. It's either increasing or decreasing, and it depends on which way the reaction is going. So we have the double arrow, which means the reaction could go either direction. If it's going to the left, then that means we're gaining this stuff and we're losing the stuff on the right. If it's going to the right, then we're gaining stuff on the right and we're losing stuff on the left. And the amount that we're gaining or losing is not a one-to-one ratio, right? Just like when we're doing stoichiometry problems, we have to look at our mole ratios. So if we gain 1 mole of N2 gas, that means we lost 2 moles of NH3, and we also gained 3 moles of H2. So if the N2 changes by 0.11 mole, how much did everything else change? Well, the H2 is going to change by 3 times that, so 0.33 moles, and the NH3 is going to change by negative twice that, and negative because the left side concentration is going down, so we're going to lose negative 0.22 moles over there. And so we can generalize this by, instead of using numbers, using x's and looking at our signs. So changes on opposite sides of the arrow have opposite sign, and the positive can be on either side, the negative can be on either side, but they're always going to be opposite on opposite sides of the arrows. And coefficients are equal to our coefficients in our balanced chemical equation. So what we have here is the ammonia example. So ammonia decomposes into nitrogen and hydrogen upon heating. So if the ammonia changes by negative 2x, then the nitrogen increases by x and the hydrogen also increases by 3x. We're just copying down our coefficients. So down here is another example. We have propane and oxygen, and we have carbon dioxide and water. And you'll notice the propane is actually increasing by x, which means our oxygen is also going to increase, but by 5x because of its coefficient. The carbon dioxide is going to decrease by 3x, and the water is going to also decrease, but by 4x. So this reaction is actually proceeding to the left because we're losing stuff on the right and gaining stuff on the left. Now, we're going to use these and ice tables to figure out what the equilibrium constants are and keep track of concentrations throughout the reaction. And ice is just a way to help us remember. We're going to have initial concentrations, changes in concentration, and then equilibrium concentration. And it is true that the initial plus the change, which we represent with delta, is equal to equilibrium. So we're going to use some basic arithmetic to help us out here. So let's look at an example problem using an ice table. This is an ice table. You'll notice across the top I have my reaction, and it's this reaction where I2 reacts with iodine ion to produce I3 minus ion. And it tells us what we start with. It says we start with 0.001 moles of each reactant. That's usually the stuff on the left. So I have my initial concentration of the stuff on the left. Run ahead and fill that in the table. And it doesn't say we start with any I3, so we're assuming we start with none of that, so this is 0. The only way this reaction can progress is to the right. So we know that the concentration on the left is going to decrease and the concentration on the right is going to increase. And since my coefficients are all 1 in this reaction, then they decrease and increase by similar amounts. It also tells us that the ending concentration of I2 is 0.000661, and that means that's also the ending concentration of I minus because they are going to change by the same amount. They have the same coefficient, 0.000661. But I need to solve x so I can find my final equilibrium concentration of I3. So what I can do is I can just pick either of I2 or I minus, and I can say 0.001 minus x equals 0.000661. And if I solve this for x, then x equals 0.001 minus 0.000661, which equals 0.000339. And now I actually have x, and 0 plus x gets me my term here, 0.000339. And now I can find my reaction quotient, QC, which is actually equal to Kc as long as we're at equilibrium, right? So if this is at equilibrium, then my reaction quotient is equal to my equilibrium constant, which is just the concentration of the product, I3, minus, divided by the concentration of the reactants, so I2 and I minus. And if I just sub in my numbers, so I have 0.000339 divided by 0.000661 times 0.000661. If I go ahead and punch that into my calculator, I get equilibrium constant of 764.4. And remember, that is a dimensionless quantity. It is fairly large, which means this reaction is going to favor the right side. It is going to head to the right because it's much bigger than 1. Now, we're going to use this to do a little bit more complex of an example problem. We've got to put things together about what we know, but it, again, isn't too hard. So under certain conditions, the equilibrium constant for the decomposition of PCl5 into PCl3 and Cl2 is 0.0211. What are the equilibrium concentrations of PCl5, PCl3, and Cl2 if the initial concentration of PCl5 was 1 molar? Okay, so they're telling us a lot of information, but I think we need to start with the balanced chemical equation. So it says the decomposition of PCl5 into PCl3 and Cl2. So I'm going to go ahead and write my equation. PCl5 decomposes, but this can go either way. So I'm going to go ahead and write my arrow into PCl3 and Cl2, so plus Cl2. Now I need to make sure my chemical equation is balanced. P is P, 5 is 5. Yeah, everything there is balanced. Okay? So that's my chemical reaction, and it's a balanced chemical equation for my reaction. And now I'm going to go ahead and do my ICE table. So my initial, my change, and my equilibrium, so I can keep track of all the information that they told us and hopefully figure out what we want to know. So it says the equilibrium constant, so Kc, is equal to 0.0211. What are the equilibrium concentrations of PCl5 and PCl3 and Cl2 if the initial concentration of PCl5 was 1 molar? So initially we had a 1 molar concentration here, and so we can assume that there's 0 here and 0 here because we weren't told any information. And let's see, this reaction is going to proceed to the right because there's no product yet, which means this is going to decrease on the left, but both of these on the right are going to increase. And so I don't know my equilibrium concentration, but I do know it's 1 minus x over here and x over here. And if we can find x, then we'll be done. Well, remember, Kc is equal to the reaction coefficient, or reaction quotient, sorry, at equilibrium, which is going to be x times x over 1 minus x, and this is equal to 0.0211. So I have x squared over 1 minus x equals 0.0211, and now I'm going to have to solve this. It's going to be a quadratic. So x squared equals 0.0211 times 1 minus x, if I multiply both sides by 1 minus x, and then I'm going to subtract stuff over and distribute. So x squared minus 0.0211 plus 0.0211x. And I'm going to use the quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. And first let's put this in standard form then. So x squared plus 0.0211x minus 0.0211 equals 0. And my calculator can solve this for me, or you can run it through the quadratic manually. But the a term is 1, the b term is 0.0211, and the c term is negative 0.0211. And if I put that through the quadratic, then I get x is equal to 0.135, or x is equal to negative 0.156. Now, one of these solutions is extraneous, and we know it's the negative. If this x is negative, then that means our concentration on the right side went down, but it can't get lower than 0. So the concentration of PCl3 is 0.135 molar. So concentration PCl3 equals 0.135 moles per liter, or molar concentration. The concentration of Cl2 is the same thing. Those are in a 1-to-1 ratio, so 0.135 molar. And the concentration of PCl5 is actually the 1 minus X, right? So that leaves me with 0.865 for its concentration. Okay, so this was a little bit more complicated because we had to do some of this math over here, but we're still just using an ICE table and the algebra that we know to solve quadratics to get our molar concentrations. Now, we're going to take this problem and we're going to look at it in a different light. Suppose a mixture initially contains 0.3 molars of 0.3 molar concentration of PCl5 and 0.1 molar of the other two things. Determine the concentrations at equilibrium if the reaction occurs under the same conditions. Under the same conditions means I have the same equilibrium constant, so 0.0211, and we're going to rewrite our balanced chemical equation again. So PCl5 can react, or this reaction can go either way, PCl3 plus PCl2. And then we'll set up our initial conditions, find our change in our equilibrium. So initially it says we have 0.3 moles of PCl5 and 0.1 moles of the other reactants, or species in the equation. I guess these are actually products the way this is written. And we're supposed to find, I guess I usually write these as lines, we're supposed to find the equilibrium concentrations. Well, usually I would say, okay, let's find our X and do that, but we don't actually know which way this reaction is going to proceed. So first we have to check. So we're going to find our quotient for our initial conditions, and that's 0.1 times 0.1 divided by 0.3, which equals 0.0333. And that's actually greater than our Kc, and it's greater than, that means our numerator is too big, which means we need this to decrease. So we're actually going to have a shift to the left, which means we're going to subtract x over here, and add x over here. Remember, those are all ones because these coefficients are all ones in our balanced chemical equation, which means our equilibrium conditions are 0.3 plus x, 0.1 minus x, and 0.1 minus x. So if we actually now set up our coefficient, our Kc table, our reaction quotient, 0.1 minus x times 0.1 minus x over 0.3 plus x, and remember this is at equilibrium, so this is equal to Kc, 0.0211. And now we have to do that algebra, so 0.1 times minus x quantity squared, right? So 0.01 minus 0.2x plus x squared, and I'm going to multiply both sides by the 0.3 plus x, so equals 0.00633 plus 0.0211x. And now I'm going to collect terms and solve this quadratic. X squared minus 0.2x minus 0.0211, so minus 0.20211x, and then 0.01 minus 0.00663 is positive 0.0037, so plus 0.00337 equals 0. And now we can run this through the quadratic. Our A term is 1, our B term is negative 0.20211, and our C term is 0.00337. And when we run that through the quadratic, we get x is equal to 0.183, or x is equal to 0.018. And which one of those is actually going to be our correct? Well, if x is 0.183 and we subtract that from 0.1, we end up with negative concentrations, and we can't really have a negative concentration. So 0.018 makes a whole lot more sense. X equals 0.018. Then what are our concentrations? Well, our concentration of PCl5 is equal to 0.3018. Our concentration of PCl3 is equal to 0.1 minus 0.018, which is 0.082, and that's also the concentration of Cl2, 0.082. Now remember, with algebra we can always check ourselves, so if we put this back into our reaction equation up here, we should get the 0.0211 that we started with. So 0.082 squared divided by 0.3018 is 0.22. So give or take a rounding error, we're within a reasonable expectation of our answer.